Good afternoon, ma'am. I am Rakshita Vidabadi, along with my team members, Apeksha Tanshal, Priya M. Chikeri, Rakshita Jia. We are presenting our project titled The Quantum Resilience of an Adaptive Hybrid Cryptography Framework for the Secure Communication System. In this presentation, I will cover the introduction and the system design architecture of our project. Today, the most secure communication can be released on the classical cryptography like an RSA. However, the advancement of an quantum computing that can be the methods became the variable and the quantum algorithm can be break the such encryptions much faster than the classical systems. To address this issue, our project can be processes a hybrid approaches that can be combined the classical encryption with an a post quantum techniques to ensure the secure and the future ready communication. Now I will explain the system designs architecture of our project. This project can be shows the working of an hybrid adaptive cryptography system. First, the user enter the message or the data. Then the system uses the adaptive selector, which can be decide the security method based on the requirements. If the normal security is enough, it is selected the classical path like an RSA. If the higher security is needed, it selected the post quantum path, Kyber. The both RSA and the Kyber are used to protect the AES key, not the actual data. The main encryption in this, the AES encryption can be applied to the actual data. AES is a fast and the efficient, so it can be used to the data encryption. In the transmission, the encrypted data is be sent through the secure communication challenges. In the receiver side, at the receiver side, the first AES decrypt happen, then it can be based on the selected path. The RSA can be decrypted the key or the Kyber can be decrypted the key. Finally, the original message is be obtained as an output. This system can be combined the speed and the security to provide the quantum resilience of any communication. In the point of an right side, this method can be demonstrate the quantum computing concept by using the quantum circuit. Here we applied the Harman gate, which can be created the superposition. The superposition means a qubit can be both 0 and the 1 at the same time. The output graph can be shows the probability of an different states like an a 0 0 and the 1 1. This the main idea of an architecture that can be combined the efficiency and the security by the AES and the data encryption and the quantum resonance of an techniques for the key protections. This complete system designs and the architecture. Now I will handle over my team mate to continue the next part.
Good morning, ma'am. Now I am here to explain about tools and technologies. We use Python in Google Colab as the main programming environment because it is easy for implementation and testing. For cryptography, we used the Python cryptography libraries to implement AES and RSA algorithm. AES is used for the secure data encryption, while RSA is used for secure key exchange. We also explored the PQ crypto library to understand the Kyber post-quantum cryptography concept and demonstrate the quantum resistance security. For the quantum computing demonstration, we used a IBM Quantum to stimulate quantum circuits and show concepts like superpositions. The project runs in both web-based and local execution environment for testing and demonstration purpose. Next, development progress. This slide shows the current progress of our project development. First, we complete the research on quantum threats, quantum computing. First, we complete the research on quantum threats and studied how quantum computing can affect a traditional cryptography system like RSA. Next, we selected the suitable tools and successfully implemented RSA cryptography and attack simulation. We also demonstrated basic quantum concepts using quantum circuits, especially superposition through IBM quantum tools. After that, we integrated the hybrid approach by combining crypto AES encryption with the Kyber post-quantum concept. Currently, we are testing the system performance, verifying encryption and decryption accuracy, and analyzing the overall security and efficiency of the framework. Next, uh, quantum resilient adaptive hybrid cryptography framework. In this slide, explain the complete workflow of our project. In the first phase, research and planning, we studied quantum threats, existing cryptographic system, and defined and project objectives. In the second phase, system design and architecture, we designed the workflow and finalized the adaptive hybrid security model. In the third phase, tools and technology selection, we selected Python cryptography libraries, PQ Crypto, and IBM Quantum Composure, and implementation and stimulation. In the phase, we developed RSA encryption and decryption, stimulated on RSA factorization attack, integrated AES encryption, and implemented the Kyber concept for the post-quantum security. In the testing and validation phase, we verified the encryption and decryption results, tested attack stimulation, and validate the quantum circuit outputs. Finally, in the analysis and optimization phase, we compared classic cryptography with the quantum resistant approach and optimized the system for better security and performance. Next, continued by Apeksha Kansha.
In the implementation slide, I explained how we implemented our project. First, we created a simple user interface where the user can enter a message. Then we implemented a RSA encryption and decryption using Python. We also showed a small attack by factoring the RSA key to explain its weakness. After that, we used AES for secure data encryption, and we also created a quantum circuit using IBM quantum to show the concepts of superposition. Then finally, we compared classical security with the quantum computing and used a hybrid approach with AES Kyber. In the next slide, system architecture. Um, in this slide, the system is divided into three parts: front end, back end processing, and analysis with output. In the first back end section, the user enters a message and selects the encryption algorithm. This interface is designed to be a simple and user friendly. Next, in the back end processing, here the system decides which encryption algorithm should be used based on the security requirement. It can use a RSA or a AES for encryption. Mm. This is the dashboard of front end we created for our project, and this is the message. It is only a front end. We have to still processing in back end process. Uh, um, The encrypted data is then securely transmitted and later decrypted when needed. Uh, in the third part, IBM processing, here we use IBM quantum tools. Here we used IBM quantum tools to stimulate a quantum circuit. This is the demonstrate how quantum computers processes information using qubits and probability restrictions. And the finally system performance analyzes it, checks the risk level, compares the classical encryption with quantum safe methods, and displays the result. Um, Finally, the system performance analysis, it checks the risk level and compares the classical encryption with quantum safe methods and displays the results. The output shows the encrypted text, decrypted text, and the time taken for the processes, and this helps us to evaluate the performance and security of the system. In the next slide, testing and validation. We show the first we created checked the whether RSA encryption and decryption work correctly. Then we tested an attack simulation to factor the RSA key for small values. And we also performed a quantum test where the output shows the probability between 0 and 1 in the quantum test. Finally, we check the complete system flow from input to encryption and output. Next slide will continued by Priya.
Result and analysis. The results of our project clearly show that while classical cryptography algorithms like RSA are still functioning, they are vulnerable to factorization-based attacks, especially with the advertisement of quantum computing. Through our quantum stimulation using PISC, we demonstrate the concept of parallel computation, where quantum system can process multiple possibilities stimulation due to their superposition. This highlights the potential capability of quantum computers of break traditional cryptography methods much faster than classical systems. To overcome these limitations, we implemented the hybrid cryptographic approach that combines the classical encryption with post-quantum technologies. The result indicates that this hybrid model significantly improves overall security while also ensuring the future readiness against the quantum threats. Our observation confirms that purely classical systems are quantum safe, where integrating the post-quantum algorithms enhances system reliances and provides a stronger defense mechanism for secure communication. Next conclusion. We designed and implement the hybrid adaptive cryptographic framework for secure communication. We demonstrated the classical encryption using RSA. We stimulated an attack shown vulnerability of traditional cryptography. We used IBM Quantum to demonstrate the quantum concept like superposition. We integrated AES for fast encryption and Kyber for the quantum safe protection. Finally, we showed how a hybrid cryptography can provide the secure future ready communication against the quantum threats. Thank you.
Okay. By the next week, you complete your that IBM quantums and try doing that analysis where it will prevent or not the hybrid keys and do your backends also. Okay.
Yes, ma'am.
Okay. And submit your rubrics to me now. Then upload this everything on the drive. Okay.
Okay, ma'am.
By next week, you have to complete this IBM quantum. Okay. Yes. Done now.
Okay, ma'am.
Okay. You guys can do it.
Yes, ma'am. Thank you, ma'am.